Hello all, welcome to the next session on computer graphics and visualization. In this video session, we will be discussing about three-dimensional geometric transformations such as the reflection transformation, 3D scaling, and 3D shearing transformation. So once we have discussed these transformations, we will be discussing what are the Opengl functions we have in order to perform the matrix operations as well as the Opengl functions to perform the 3D transformations. After that, we will also be looking into the working or examples for using this Opengl function. So let us begin with the first 3D transformation of this session, that is the 3D scaling or the three-dimensional scaling. So what is 3D scaling? As we've already discussed in the previous module, scaling transformation causes the change in the dimensions of the object. We can enlarge an object or we can reduce the size of the object using the scaling transformations. So if we are applying the 3D, scaling transformation to a 3D object, we call it as three-dimensional scaling. The matrix expression for the 3D scaling transformation of a position P is given by the following matrix operations. Every point position in a 3D space is specified something like this, using the x coordinate value, the y component, as well as the z component or the z coordinate value. So every point in a 3D space is given by x, y, z. Because there are three axes that we need to consider: the x axis for the left and right, the y axis for the top and bottom, and the z axis for the near and far values. So if you want to scale this particular point x, y, z, this is the transformation sequence, or this is the matrix multiplication that we need to do. So the x, y, z, the actual position, the original coordinates of the point P is multiplied with the scaling matrix. So what is the scaling matrix? Sx 0, 0, 0, 0 sy 0, 0, 0, 0 sz 0, and 0, 0, 0, 1. Observe, this is a 4 by 4 matrix. So what is a 4 by 4 matrix, or why do we need to use the 4 by 4 matrix? Because we will be using the homogeneous representations here, right? So almost all the transformation matrices that we'll be dealing with, that will be a 4 by 4 matrix. And also, since it's a homogeneous representation, we add a 1 here to this particular row. So the point x, y, z, we are going to multiply it with this scaling matrix in order to get a transformed point, right? So after the scaling matrix is applied or multiplied to this matrix over here for a given point, that particular point will be scaled, where x dash, y dash, and z dash are the scaled coordinates. Now what are these sx, sy, and sz? These are called as the scaling parameters. So sx is the scaling parameter along the x-axis, sy is the scaling parameter along y-axis, and sz is the scaling parameter along z-axis. So by multiplying the x, y, z coordinates in the column major order with a scaling matrix yields us the scaled position of a given point P. So we can represent the matrix transformation something like this, or the scaling transformation using this transformation sequence. The 3D scaling transformation for a point position can be represented as P dash is equal to S dot P, where P is the column matrix that we just discussed and S is the scaling matrix. This is a 4 by 4 matrix that is used in order to scale a given point. So after scaling, the new point that we get is represented by P dash. The scaling parameters Sx, Sy, and Sz in the matrix here, they are assigned any positive values. Now the explicit expressions for the scaling transformation relative to the origin are x dash is given as x into Sx, y dash is given as y into Sy, and z dash is given as z into Sz, right? Now let us see how to scale a given object with respect to a fixed point. So whatever scaling we just discussed now, that was about the origin. Now suppose we want to scale a given point scale a given object with respect to some other fixed point. So we need to follow a bunch of steps there. Now since graphics packages provide only a routine that scales relative to the coordinate origin, we can always construct a scaling transformation with respect to any selected fixed position given as xf, yf, zf using the following transformation sequence. Now let us see what the transformation sequence or the steps we need to follow to scale a given object with respect to a fixed position xf, yf and zf. The first step in this transformation sequence is to translate the fixed pointer to the origin. So we need to first perform the translation transformation. We need to translate the fixed pointer to the origin. That is the first step in our transformation sequence. The second step is to apply the scaling transformation relative to the coordinate origin. So here in the second step we need to apply the scaling transformation relative to the coordinate origin. And the last step is to translate the fixed point back to its original position. So these are the three steps that we need to perform in order to scale a given object with respect to a fixed point xf, yf, zf. Let's look at that particular sequence of transformation using this particular example. Suppose we want to transform this particular 3D object with respect to the fixed point xf, yf and zf. So what do? We translate the object to the origin, scale the object with respect to the origin, and then perform a translation so that the object is moved back to the fixed point xf, yf and zf. Right? So this is a three-dimensional scaling transformation. So this is the original position. First step is perform the translation. So move the object to the origin. Second step. So this is the first step. We translate the object to the origin. This is the second step. We scale the object at the origin. Third step, perform the inverse translation. What do you mean by inverse translation? Whatever translation that you have performed, you are going to undo it. So move the object back to the fixed point. So this is the transformation sequence for scaling an object or a 3D object with respect to a fixed point xf, yf, zf. So if you look at the matrix transformations or the matrix operations, this is what we are going to do. So we need to translate the object with respect to the fixed point. We need to scale the object, and then we need to perform the inverse translations, right? So this is the sequence of transformation. This is step 1, step 2 and step 3. So these are the three matrices that need to be multiplied in order to scale a given 3D object with respect to a fixed point xf, yf, zf. So if you multiply these three matrices, this is the transformation matrix that we are going to get, the concatenated matrix. Okay, so sx 0, 0, 1 minus sx into xf, 0 sy 0 into 1 minus spy yf, 0, 0 sz into 1 minus z sz into zf, and 0, 0, 0, 1. Again, this is a 4 by 4 transformation matrix. So that was about the three-dimensional scaling. So scaling transformation causes the object to either enlarge or reduce its size. So we can translate or we can scale a given 3D object with respect to the origin, or we can scale a given 3D object with respect to a fixed point xf, yf and zf, or xf, yf, zf. Let us move on to the next type of 3D transformation, that is a reflection transformation. So what do you mean by reflection transformation? Reflection transformation creates a mirror image of a given object. So that is what we call as a reflection transformation. A reflection in 3D space can be performed relative to the selected reflection axis or with respect to the reflection plane. So in 3D space, we can perform the reflection with respect to a particular reflection axis, that is x, y or z axis, or also with respect to a given reflection plane. Reflection with respect to a plane are similar when the reflection plane is a coordinate plane. So we can have three planes there: reflection with respect to xy plane, the xz plane and the yz plane. So reflection with respect to these planes, we can think of the transformation as a 180-degree rotation in a 4D space with a conversion between a left-handed frame to a right-handed frame. Let us look at one example here. So this is an example for reflection relative to the xy plane. Whenever we are performing the reflection with respect to the xy plane, the xy plane acts like a mirror, and this z-axis value will be converted to the opposite value, the negative value, right? So reflection with respect to the xy plane causes the z coordinate value to be converted into negative values. The direction of z-axis will be changed here. It will be in the opposite direction. So that is because the xy plane acts like a mirror. Okay, that is an example for reflection with respect to the xy plane. Now the matrix representation for this reflection relative to the xy plane is given as 1 because the direction of z-axis has now changed. So 0 0 minus 1 0 and 0 0 0 1. So this is an example for the matrix which is used to represent the reflection relative to the xy plane. Whatever plane about which we are going to perform the reflection, that plane acts like a mirror. Okay, and the remaining axis will be converted to its opposite direction. So z coordinate value will be converted to negative z coordinates. So that is what is specified in this particular matrix. This row represents the z coordinate value that will be converted to a negative value. That is about the reflection relative to the xy plane, and this is the corresponding matrix. Now let us move on to the next type of 3D transformation, that is the shearing transformation. Now shearing transformation can be used to modify the shape of the objects. Shearing transformation, it changes the shape of the object or it distorts the shape of the object. For a three-dimensional space, we can also generate shears relative to the z-axis as well. General z-axis shearing transformation relative to a selected reference position is produced with the following matrix. So this is a matrix that represents the general z-axis shearing transformation relative to a reference position, selected reference position, that is z reference. So what is this matrix? 1 0 shearing factor along shearing factor zx, so minus shearing factor zx into the z reference, 0 1 shzy minus hszy into z reference, 0 0 1 0 and 0 0 0 1. So this is a matrix that represents a general shearing transformation relative to a selected reference position. So the below diagram here, it shows us the shear transformation for a given cube, right? So we are shearing a cube. It's as if we are pulling the cube away from us, right? So this is a unit cube sheared relative to the origin with the shearing parameter s h zx and s h zy equals to 1, right? So in both the direction, in x direction as well as the y direction, the cube will be pulled towards it. So we get a view as if the cube is pulled away from us. So that is the shearing transformation. This was the original unit cube. So after applying the transformation, this is a transformed cube after applying the shearing transformation. Now let us look at the Opengl geometric transformation functions. So we discussed the three basic geometric transformations earlier, right? So it was translation, it was rotation, and one more was the scaling. Okay, translation, rotation, and scaling are the basic 3D geometric transformations. In order to implement these translations in Opengl or transformations in Opengl, we have a bunch of Opengl functions. So let us first look into the Opengl function for performing the translation transformation. A 4x4 translation matrix is constructed with the following routine. The name of the function is GL translate followed by a suffix, and it accepts three parameters. What are these three parameters? Tx, Ty and Tz. Now in place of the suffix, we can either replace it with f or d. F stands for floating point data type and d stands for double. And it accepts three parameters, Tx, Ty and Tz, which are the translation parameters along the x-axis, the y-axis and the z-axis. Now this Tx, Ty and Tz can be assigned any real number of values. Okay. For a 2D application or for two-dimensional application, we set the translation parameter along the z-axis as 0, because for 2D application there is no concept of z-axis. We have only x and y-axis. For if you're using this particular function in a 2D space, in that case this value of translation parameter tz will be assigned the value of 0. And the 2D position is represented as a 4-element column matrix with the z component equal to 0. So we have the same function for 3D as well as 2D applications. In case of 2D application, we set the translation parameter along the z-axis equal to 0. So here's an example. The GL translate f represents the floating point type. So Tx value is assigned the value of 25, Ty value is assigned the value of -10, and Tz is assigned the value 0. So this indicates we are not specifying a non-zero value to the z-axis or the translation parameter along the z-axis. We have initialized the value equals to 0. So this is how we will be using this GL translate function in case of a 2D application. So remember, the name of the function for specifying the translation transformation is GL translate. It accepts two suffixes, f for floating point and d for double, and it accepts three parameters, tx, ty and tz, which are the translation parameters along the x-axis, the y-axis and the z-axis. Okay, now let us look into the next OpenGL transformation. The geometric transformation function that we have is the GL rotate. As the name suggests, this OpenGL function is used to perform the rotation transformation. So a 4 by 4 rotation matrix is generated with the OpenGL function GL rotate, which accepts four parameters. So what are these four parameters? The first parameter is the angle of rotation theta, and the next three parameters specifies about which axis are we going to rotate a given object, right? So the vector v can be represented as vx, vy and vz, and they can have any floating point value for its components. The vector defines the orientation for the rotation axis that passes through the coordinate origin. Suppose I specify a function something like this, GL rotate, and in place of this suffix here we can have f or d depending upon the data type. So the angle of rotation theta will be 90. So Vx will be 0, Vy will be 0 and Vz will be equals to 1. That indicates we are going to rotate a given object by 90 degree about the z-axis. So that is what it indicates, right? Remember, the function for performing rotation transformation in OpenGL is the GL rotate. So that is a function for performing the OpenGL rotation geometric transformation. It accepts four parameters. First parameter is the angle theta, which specifies the angle of rotation, followed by three values Vx, Vy and Vz, which specifies about which axis are we going to perform the rotation. So GL rotate function is used to perform the geometric rotation transformation. Similarly, we have one more function called as GL scale, which performs the scaling transformation. So we obtain a 4 by 4 scaling matrix with respect to the coordinate origin with the following routine. The name of the function is GL scale. Again, it accepts the suffix f or d, and it accepts three parameters. What are those three parameters? Sx, sy and sz. Now the suffix code is again f or d depending upon what type of data are we dealing with, and the scaling parameters sx, sy and sz can be assigned any real number values. Now scaling in two-dimensional system involves changing in the x and y dimensions. So a typical two-dimensional scaling operation has a z scaling factor equals to 1. Remember, we have these functions which are applicable for 2D as well as 3D systems. So whenever we are dealing with 3D systems, you can set any value for Sx, Sy and Sz. But when it comes to 2D applications, Sx and Sy we can specify any real number values. But for Sz, that is the Z scaling factor, we set the value equals to 1.0. That is only for two-dimensional operations. So scaling in two-dimensional system involves changes in the x and y dimensions. So typical 2D scaling operation has a Z scaling factor equals to 1. So this is an example here of using the GL scale function. So GL scale f, scaling factor along x-axis is 2, scaling factor along y-axis is -3, and scaling factor along z-axis is equal to 1. So remember, we discussed three OpenGL geometric transformation functions. What are those? We discussed GL translate, GL rotate and GL scale. Now let us proceed and to understand what we mean by OpenGL matrix transformations. The default argument for the GL matrix mode function is the GL model view. So whenever we are going to specify the modeling and viewing details in our program, so we need to set the current matrix mode to a GL model view, which is the default matrix mode. So the default argument to the GL matrix mode function. So GL matrix mode function is used to set the current matrix. Once we are in the model view mode or any other mode, a call to the transformation routine generates a matrix that is multiplied by the current matrix for that particular mode. Suppose the default model matrix is the model view matrix. We need to initialize this matrix with a bunch of values. To do that, we have a set of OpenGL functions. In addition, we can assign values to the elements of the current matrix, and there are two functions in OpenGL library for this particular purpose. So first function that we have is a GL load identity. So we can select a particular matrix as a current matrix, and once we have done that using the GL matrix mode function, we can call the GL load identity function to assign the identity matrix to the current matrix. Suppose I write GL matrix mode and the parameter as GL model view, and after that if I invoke the function GL load identity, GL model view matrix will be assigned with an identity matrix. So that is what this GL load identity function do. It assigns an identity matrix to the current matrix. The current matrix can be anything. It can be model view matrix, it can be projection matrix, and so on. So GL load identity matrix assigns identity matrix to the current matrix. That is one way. Now there's one more way where we can assign other values to the elements of the current matrix other than the identity matrix. Now suppose we don't want to assign identity matrix to the current matrix, but we want to assign some of the elements to the current matrix. In that case, we need to use one more function called as GL load matrix. Okay, that is the name of the function, GL load matrix, and it accepts an array name which contains 16 elements as a parameter. Remember, GL load matrix is a function which is used to assign some values or assign some elements to the current matrix other than the identity matrix. It accepts one parameter which is the name of an array which contains 16 elements. Why 16 elements? Because we are always dealing with 4 by 4 matrices. 4 rows and 4 columns, total 16 elements, right? A single subscripted 16 element array of floating point values is specified with parameter elements of 16, and a suffix code of either F or D is used to designate the data type. Similarly, what we discussed in the previous slides. So here the suffix can either be F or D depending upon the data type that we want to use. The elements in this array, in this case the array name is elements 18, must be specified in the column major order. What do you mean by column major order? We first list the 4 elements in the first column, then we list the next 4 elements in the second column, the third column, and finally the fourth column. That is called the column major order. So whatever array that we are specifying here, that must be specified in the column major order. It should contain 16 elements. Column major order indicates we first specify the first column elements, the second column elements, third, and finally the fourth column elements. Let us look at one example to illustrate this GL load matrix function. Okay, so we are changing the current matrix to GL model view using this particular line here. So once we have set the current matrix as GL model view, now let us say we want to fill this GL model view, or we want to assign 16 elements starting from 0 to 15 to this GL model view matrix. For that case, we need to first declare an array containing 16 elements. That is what we are doing here. This is a declaration of an array containing 16 elements. So here we are declaring a looping a variable that is used for looping. So we use the for loop for k equals to 0, k less than 16, k plus plus, elements of k equals to float of k. So what will k contain? 16 elements starting from 0 to 50. Now we need to specify that, or we need to copy these 16 elements which is present in the elements of array into the matrix GL model view. How do you do that? Using the function GL load matrix. Since the data type of that particular array is floating type, so GL load matrix F is a suffix and the name of the array. So this will cause the model view matrix to be something like this, right? The model view matrix will contain the elements something like this in the column major order. So the first column that we have here, the second column, third column, and the fourth column. So these are the elements, 16 elements that will be loaded or assigned to the matrix GL model view. The model view matrix will contain these 16 elements. What is the function you have used? The function you have used is GL load matrix. To set the current matrix, you are using the function GL matrix mode. If you want to set this GL model view to be containing the identity matrix, in that case you don't have to write all these things. You can just replace all these things with a single function name, that is GL load identity. That will assign the current matrix to the identity, or that will assign the identity matrix to the current matrix. The current matrix will contain the identity matrix if you're using the GL load identity function. If you don't want to use identity matrix and if you want to specify some other elements, in that case you need to use the function GL load matrix. So remember, for matrix operations we discussed 3 functions till now. What were those 3 functions? We discussed the GL load matrix function, the GL matrix mode, the GL load identity, and the GL load matrix functions. Now we can also concatenate the specified matrix with the current matrix. Whatever current matrix that we have, we can concatenate it. We can post multiply it with some other matrix. To do that, you have an OpenGL function called as GL multiply matrix. The name of the function is GLU multiply, that is MULT matrix. and again it accepts F or D as the suffix depending upon data type, and accepts an array containing 16 elements as a parameter. It accepts an array name which contains 16 elements as a parameter. So this will concatenate the current matrix with a specified matrix. The current matrix is post multiplied by the matrix specified in the GL multiply matrix, and this product replaces the current matrix. Thus, assuming the current matrix is the model view matrix, okay, which we designate as M, then we update the model view matrix something like, which is computed as M equals to M into M dash, where M dash is the matrix with which you are going to multiply the current matrix, and whatever the product that you are going to get, that will be set as the current matrix. That is called as the post multiplication. That is what is mentioned here. So if you want to multiply the current matrix with some other matrix, you need to use a function called as GL multiply matrix. It accepts a single parameter, which is again an array name containing 16 elements. Now OpenGL also supports model with stack depth of at least 32 value or 32 elements or 32 size, right? So you have a function called as GL get integer v, and it accepts two parameters. So GL max model view stack depth and stack size. So this determines the number of positions available in the model view stack for a particular implementation of OpenGL. Now suppose we want to get how many positions are available in the model view stack for a particular implementation of OpenGL. We have one more OpenGL matrix operation function called as a GL get integer v. The parameter that you are going to specify is GL max model view stack depth, comma stack size. It returns a single integer value to the array stack size. Now in place of this particular symbolic constant, you can use these symbolic constants as well. So for projection matrix, you have GL max projection stack depth. For texture matrix, you have GL max texture stack depth, and for the color matrix, you have GL max color stack depth. So we can also find out how many matrices are currently in the stack using the same function GL get integer v, but we need to change the parameters. So what is the parameter we are going to change? GL model view stack depth, comma number of matrices. This will give us how many matrices are currently in the stack. So matrices will be stored in the form of stack. If you want to get how many matrices are present in the stack, you can do that using this get integer vector function, again get integer v. The parameters are GL model view stack depth, comma number of matrices. So this OpenGL function called as GL get integer v, it is used to calculate, or we can use this function to find out how many number of positions are available in the model view stack or a given stack for a particular implementation of OpenGL, as well as how many matrices are currently present in a given stack. So that is the usage of this GL get integer v function. And lastly, we have two functions for matrix operations in OpenGL: GL push matrix and GL pop matrix. As we are all aware, stack is the data type which is famous for two operations, right? So push operation and pop operation. So stack is a last in first out kind of a data structure. So removing an element from the stack, we call it as pop operation. Adding an element to a stack, we call it as a push operation. So we have two functions available in OpenGL for processing the matrices in a stack. First function you have is GL push matrix. So this function copies the current matrix at the top of the active stack and stores that copy in the second stack position, right? So GL push matrix copies the current matrix at the top of the active stack and stores that copy in the second stack position. You have one more function, GL pop matrix, which destroys the matrix at the top of the stack, and the second matrix in the stack becomes the current matrix. So these are the two functions to perform the push and pop operations on the matrix stack. So we discussed a bunch of OpenGL matrix operations. We started with the GL matrix mode function. Then we had the GL load identity function, which was used to assign identity matrix to the current matrix. So we discussed one more function called as the GL load matrix, which is used to assign some other elements or some other matrix as the current matrix. It accepts one parameter, which is the name of an array which contains 16 elements specified in the column major order. So we looked at one example for using the GL load matrix function. So if you want to multiply the current matrix with some other matrix, so for that you have an OpenGL function called as GL multiply matrix, and again it accepts an array name which contains 16 elements as the parameter. So it is used to post multiply the current matrix with some other matrix. And then we discuss the OpenGL matrix function called as GL get integer v, which is used to retrieve the number of positions available in a given stack for a particular implementation of OpenGL. We can also use this GL get integer v function to retrieve the number of positions or how many matrices are currently present in a given stack. And lastly, we have two functions, GL push matrix and GL pop matrix, which are used to push and pop the matrices in a given OpenGL stack. So these are the things we discussed. In today's class, we discussed what do we mean by the scaling transform, 3D scaling geometric 3D transformation, such as scaling. We discuss 3D transformation called as reflection and shearing, and then we discussed what do we mean by uh, what are the OpenGL functions we have for geometric transformation. We discussed GL translate function, GL rotate function, and GL scale function, followed by the OpenGL matrix operations, such as the functions such as GL load identity, GL load matrix, GL get integer v, GL multiply matrix, and GL push matrix and GL pop matrix. With this, let us conclude this video session. Thank you.